So this video we're looking at systems and centre of mass. So first of all, I'm going to go down those bullet points. The centre of mass defined if you have an object, a random object. There's a point somewhere down the centre where you could balance it on a pivot point and it wouldn't fall off either way. So that's centre of mass is in that line of balance. Interestingly, to find an object that's a bit oddly shaped, if you balance it through two different planes, so say you take an object like this, you balance it once, you get a line here, and then you tip it on its end. How can I do that on here? I don't know, I could probably rotate objects, but I don't know how. But here's the same object balanced in a different way. Those two lines of intersection, with that being the second one here, that gives you the centre of mass for a two-dimensional object. And you can take a third line of balance to find the centre of mass of a three-dimensional object, and presumably fourth for a four-dimensional object. So the centre of mass is defined, I guess, as the point where the weight bears down, or you could call it the balance point where it balances nicely. Okay, centre of mass of a system. A good example to use for this might be planets. Here's the Earth, and here's the Moon, 300,000 kilometres between them. If we were to consider that, you might be thinking, how could you even begin to balance that? But if we imagine that they're joined from centre of mass of each individual part to the centre of mass of the other, we would find that there would be a hypothetical balance point somewhere there, and I believe it's inside the centre, inside the Earth's surface. So that's how we would deal with a system. A system is a kind of combined number of objects, obviously more than one. They don't have to be connected, as we can see here, by anything physical, but they've got to obviously have some sort of relationship. In the case of the Earth-Moon system, they've got a link through gravity, and they rotate actually about that centre of mass, and this plays into the gravitation a little bit later. So I think you get the idea of what a system is and what centre of mass is and how those two can link together. We now come to the point where we look at calculations and the links to torque. You might have worked out the links to the torque. I'll just give you that very quickly. But if you're balancing even the Earth-Moon system on a point, if that could be done, there's a smaller mass and a larger distance, which in a sense are balancing or pulling, kind of like a torque, force times distance, remember, Fd. And on the other side, a shorter distance but a larger mass or the larger force. And those two are balanced, equal and opposite, and that's how you find the centre of mass of a system. There's a kind of intuitive thing about that, and you can work it through an Earth's gravity with an object that might be balancing to really come to a firm conclusion on that. But we're just going to go with the intuitive one for now. The calculations then, as you might imagine, will be, I'll just use this example right here, Earth-Moon. No, I won't. I'll redraw it, give you more space. Here's the Earth. Here is the light connection, Earth and the Moon. And for the sake of this, I'm just going to give you a hypothetical centre of mass closer to the larger mass, COM. Now we're going to have a distance x1, and I'll call this m1 actually rather than moon 1, and another distance x2, and this can be m2 for mass 2. Now you can apply it to any situation you like. So obviously mass 2 is larger. Mass 2 times x2 is going to be equal to mass 1 times x1. So that's what you would expect from the torque idea. Torque though is a force times a distance, not just a mass times a distance. If they're both under the same gravity, then it'll reduce to mass times distance equaling mass times distance. You can work that one out on your own. Another way that may be helpful to formulate this equation is to rearrange it so you've got m2 over m1 equals x1 over x2. Do you see the reverse ratio of each? That shows there's an inverse proportional relationship of the mass compared to its own distance in relation to the other. Now, I'm just going to give you one trick that I've come across that has sometimes proven helpful. I'll give you two. One is you can sometimes take a pivot point and then measure all your distances from there. So that would be one distance, and there's another distance. And so you've got the centre of mass of the whole acting through there. The mass of the entire system acting through there, and the mass of that second one acting at that distance. anyway, you can play around with the different things like that. Something's bugging me about that. I might have misspoken, but in any case, taking a pivot point and using your equilibrium may be a way that you can solve problems, or intuitively work better with the system. Also, taking an external pivot point and just measuring everything from a kind of a random point that's got an additional distance could also prove helpful. Okay, yeah, just keep your eye open, because they always throw out slightly different ones with this. It might be that you've got your two spaceships and you happen to have an astronaut outside of it over here, and that's why where that situation might come up. But that's the gist of it. We've covered what centre of mass is, what a system is, and we've looked at the formulas, and they're simple formulas. You just have to know when to apply them, where those distances are, and do your calculations with diligence and discipline so that you don't make little silly mistakes. There you go.